Welcome to Brain Vision.
Hi everyone. So what we have is a 0.3 meter cube volume tank containing R134A at 14 degrees Celsius. The 55% of the mass is in the vapor phase and the rest in the liquid phase. So we have a quality of 55%. And we have a supply line that's at 1.4 megapascals and 100 degrees Celsius. And we know that at 1 megapascal inside this rigid tank, there's only vapor, and then the valve closes to the supply line. So what we're asked to find is the final temperature inside the tank, the mass of refrigerant that has entered the tank, and the heat transfer between the system and the surroundings. So what we're going to do first is just write down all of our properties that are located in the thermodynamics tables, A11 through A13. So we know that at state 1, the temperature is equal to 14 degrees C, and our quality is 0.55. So what we can do is actually go ahead and solve for our specific volume using these two quantities and the pressure that we also know. And we find that we can actually write the specific volume at 1 as equal to V1 equals Vf plus X VFG. And Vf and VFG are quantities that we can get from the table. And X, as we know, is 55%. So this gives us a specific volume at 1 of 0.02427 meters cubed per kilogram. We can use a similar equation to solve for the internal energy. We can say that U1 is equal to UF plus X1, UFG. UF and UFG are quantities that we can get from the table. X1 is 55%. So this gives us a specific internal energy of 162.57 kilojoules per kilogram. Now these are at state 1. Now what we can do is actually go ahead and solve for our properties at state 2. We know that the property at state 2, pressure is 1 megapascal. That's given in the problem. And we also know that it is a saturated vapor. So using these two known values, we can actually go ahead and solve for our specific volume at 2. So we know that V2 is just going to be equal to Vg at 1 MPa, and that quantity is equal to 0.02033 cubic meter per kilogram. Likewise, U2, our specific internal energy, will be equal to Ug at 1 MPa, which is equal to 250.71 kilojoules per kilogram. Now we have to look at the refrigerant that is entering the rigid container. So we know that Pi, which we're going to solve, we're going to represent the pressure of the supply line, is equal to 1.4 MPa, and Ti is going to equal 100 degrees C. Using these two information, we can find the entering enthalpy. Specific enthalpy is equal to 330.32 kilojoules per kilogram. What we're going to do now is define our system. So we can define the mass as we define the tank as our system and as a control volume. So what we can do is write a mass balance and say that the mass coming in minus the mass coming out is equal to the change in mass of the system. As you know, there's actually no mass leaving. All we have is mass entering. So that's going to be Mi is equal to mass 2 minus M1. Next, what we're going to do is an energy balance and say that energy coming in minus the energy coming out is equal to the change in energy of the system. Now, we have heat transfer. We're going to assume that's positive coming in. We also have mass coming in as well. So that's going to increase our specific enthalpy and energy. So that's going to be MIHI. There is no heat transfer leaving. So that's going to be, E out is going to be 0. And that's going to be equal to our change in system energy. So that's going to be M2 U2 minus M1 U1. So we know that first thing we're asked to solve for is the final temperature of the tank. So we know that the tank only contains saturated vapor at its final state. and therefore the final temperature is just the saturation temperature at this pressure. So we know that T2 is going to be equal to T saturation at 1 MPa, which is going to be equal to 39.4 degrees Celsius. So that is our final temperature of the tank. Next, what we're going to do is solve for the mass of the refrigerant that has entered the tank. So we know we can actually solve for the mass in the beginning and the mass at the end by using the definition of specific volume. So remember that specific volume is just the total volume over the mass. So rearranging this and bringing the mass and to the other side, and the specific volume to the side with the volume, we can rearrange this to say that mass is equal to total volume over specific volume. So in the terms of the variables that we have, the initial mass will be equal to the total volume over the specific volume at 1, and that'll be equal to 12.36 kilograms. Mass 2 will be equal to the total volume over specific volume at 2, which we can calculate and see that it's equal to 14.76 kilograms. So, as we defined before in the mass balance, the mass entering is simply M2 minus M1, and we actually have these two quantities that we just solved for, and this gives us a mass that has entered the tank of 2.396 kilograms. That's the mass that has entered. Now, the last thing we have to solve for is the heat transfer that has occurred during this process. So remember, our heat energy balance was Q plus MI HI is equal to M2 U2 minus M1 U1. Now we solve for Q, so Q is going to be equal to M2 U2 minus M1 U1 minus MI HI. So we actually have all of these quantities, and just plugging in for these variables gives us a total heat transfer of 899 kilojoules. That is our final answer.